Hello, everyone. Welcome to my talk titled Distributed Quantum Inner Product Estimation. This is joint work with Anurag Anshu at Harvard and Zeph Landau at UC Berkeley. So let's consider the following problem. Alice has k copies of an unknown mixed state rho, and Bob has k copies of an unknown mixed state sigma. Their goal is to estimate the inner product of the states trace rho sigma up to some finite additive error, using only local quantum operations and classical communication. So in this talk, we will show the optimal sample complexity of this task, which is the smallest k, such that this task is achievable. So here, k could depend on two parameters: the dimension of the quantum states, d, as well as the desired additive error, epsilon. So here are some quick thoughts about this problem. First, what happens if we allow quantum communication in the problem setting? The answer is only 1 over epsilon squared copies suffices. This is because Alice can just send her copies to Bob, and then Bob performs the swap test to estimate the inner product. Here, the swap test refers to these well-known quantum circuits for estimating the inner product. However, because of the classical communication constraint in our problem definition, the swap test cannot be performed in our problem. Second, why do we care about trace rho sigma? The answer is trace rho sigma itself doesn't have much operational meaning, but there are 2 points. First, when one of the states is a pure state, then trace rho sigma equals the fidelity between rho and sigma, which is a standard metric in quantum information. And second, trace rho sigma is related to several other non-standard distance metrics, such as the Hilbert-Schmidt distance and the geometric mean fidelity. So we can see that these distance metrics are determined by trace rho sigma, trace rho squared, and trace sigma squared. So in our setting, Alice and Bob needs to estimate trace rho sigma, and then they can estimate trace rho squared and trace sigma squared locally, and finally they can compute the above quantities. Third, why do we care about estimating trace rho sigma in a distributed setting? So the motivation of our problem comes from a benchmarking task known as cross-platform verification, proposed by Alban et al. So here the situation is the following. Alice has some unknown quantum states prepared on a superconducting qubit device, and Bob has some unknown quantum states prepared using linear optics. And they are wondering, how do we compare our unknown quantum states that live on different physical platforms? So with our current technology, we don't have the ability to perform a joint quantum operation across the two different physical platforms, such as the swap test. And therefore, this motivates our problem setting for distributed quantum inner product estimation, which only allows classical communication. So the next observation is that the answer to the optimal sample complexity of this task probably depends on the model of measurement and communication allowed in the protocol. So what I mean here is the following. Let's consider the most naive algorithm for this problem, where Alice and Bob just performs quantum state tomography and then compute trace rho sigma. So in this case, the sample complexity of this task just equals to the sample complexity of quantum state tomography. And it is well known that the sample complexity of tomography depend on how we are allowed to measure the quantum states. In particular, if we only allow single copy measurements, where the states are measured 1 copy at a time, then it requires theta d cube copies to perform quantum state tomography. On the other hand, if we allow multi-copy measurements, where multiple copies of the state can be measured at the same time, then it only requires theta d squared copies for tomography. Of course, tomography is not the optimal algorithm for our problem, but this example gives evidence that the answer to the optimal sample complexity of our task could depend on whether we allow single copy measurements or multi-copy measurements. In addition, because our task involves classical communication, we know that the complexity could also depend on how Alice and Bob are allowed to communicate. In the weakest setting, called simultaneous message passing, Alice and Bob are only allowed to send one message to a third party, who then computes a function. A stronger setting is one-way communication, where Alice sends a message to Bob, and then Bob can measure his states based on the message. The most general setting is interactive communication, where Alice and Bob can communicate multiple rounds and perform adaptive measurements. So we have introduced 2 models for measurements and 3 models for communication. And a priori, the above 6 models could all lead to different sample complexity of this task. But interestingly, our main result is to show that this is not the case. So our main result is the following. The optimal sample complexity for distributed quantum inner product estimation is theta maximum of 1 over epsilon squared and square root d over epsilon. And this holds across all measurement and communication models introduced above. In particular, when epsilon is a constant, the result gives k equals theta 2 to the n over 2, where n is number of qubits. So let's try to understand what this result means. First, regarding the cross-platform verification task, we conclude that it requires less samples than tomography, which is square root d versus d squared or d cubed. However, the result also implies that this task still requires exponential samples in the number of qubits, even with the most powerful measurements allowed by quantum mechanics. This means that this task is not scalable in general. Second, let's focus on this sample complexity itself. So the lesson we learned from shadow tomography is that linear functions of an unknown quantum state can be estimated sample efficiently. However, our result shows that our task is not sample efficient. And the reason could be the classical communication constraint seems to be a barrier for achieving sample efficiency. And finally, let's focus on the fact that the result doesn't change across all measurement and communication models. So this is in contrast with several known results, because besides tomography, we also have many other examples that are known, which demonstrate large separations between single and multi-copy measurements for quantum property testing of a single system, as shown by these previous works. However, in our distributed setting, we know that access to multi-copy measurements does not provide an advantage in this task. So it is an intriguing open question to study whether this behavior is only true for the inner product or is true in general. Next, we will show a proof sketch of our main result. So to prove our main results, we only need to prove 2 bounds. First, we want to prove that using single copy measurements and simultaneous message passing, which is the weakest model, Alice and Bob can estimate inner product with this sample complexity. And second, even with multi-copy measurements and interactive communication, which is the strongest model, Alice and Bob still requires at least this sample complexity to estimate inner product. So let's start with the upper bound. So To prove the upper bound, here the main idea is to reduce quantum inner product to classical inner product using an algorithm called correlated classical shadows. So as a warm-up, let's start with how do we estimate the inner product of two classical discrete probability distributions? So let's consider a very simple problem. We are given two unknown probability distributions, P and Q, supported on D elements. And we are allowed to draw IID samples from them. And the goal is to estimate the inner product of the two distributions. So a very simple algorithm is the following. We just draw M samples each from the two distributions, and then compute this quantity, which we can call collision estimator. So this function just counts for every pair of the samples drawn, how many collisions are among the pairs. For example, if we consider this example of the two sets of 4 samples from the two distributions, after counting collisions, we realize there are 3 pairs of collision. So we output 3/16 as our estimator for the inner product. Actually, this can be proven to be the optimal algorithm for estimating inner product. So in our quantum inner product estimation task, we can reduce to classical case by using the following algorithm. So first, Alice and Bob use some shared randomness to generate a random unitary matrix U. So here, it is important that they share the same random unitary, which is what we mean by correlated classical shadows. And next, Alice and Bob just apply this same unitary U to each copy of their states. And next, they just measure each copy of their states in the computational basis and obtain a set of bit strings. And next, Alice and Bob can just use the collision estimator, where they count the number of pairwise collisions between A and B. And they can compute a function of the number of collisions as an estimator of the inner product. So why does this algorithm work? In particular, if we want to prove the sample complexity bound for this algorithm, we need to calculate the variance of the above estimator, which is somewhat complicated. But below, we will give some intuitions of why square root D is the correct bound. So the intuition actually comes from birthday paradox, where we know that we expect to see collisions after drawing square root D samples from a uniform distribution on D elements. Well, in our problem, the situation has a similar behavior. So we know that because the unitary U is random, Alice and Bob's measurement outcome distributions are close to uniform. And therefore, if the number of samples is less than square root D, both Alice and Bob never see any collision in their measurement outcomes. However, when the number of samples is all square root D, then Alice and Bob can expect to see more collisions when the inner product between their quantum states is large. And correspondingly, they expect to see fewer collisions when the inner product between their quantum states is small. And therefore, this can be viewed as an estimator for the inner product of their quantum states. And this finishes the proof. Next, we move on to prove the lower bound, which is in the strongest model with multi-copy measurements and interactive communication. Alice and Bob still requires this sample complexity to estimate. So for this proof, we will focus on a simpler problem. And here, Alice and Bob have a decision problem. They are promised that one of the following 2 cases hold. First, Alice and Bob both share the same have a random pure state phi, and they both have k copies. And in the second case, Alice and Bob also both have k copies of a random pure state, but these states are independent. So the difference is that in case one, they always have the same random state. And in case two, they always have independently random pure state. So their task is to distinguish which case they are in with the smallest number of samples possible. So this problem is a special case of our original problem, because in case one, their inner product is always equal to 1. And in case two, their inner product is exponentially small with high probability. And therefore, we only need to prove a lower bound for this problem. And here, we will prove a lower bound that the above problem requires at least square root d copies to decide. And the idea to prove this lower bound comes from the symmetric subspace. In particular, when we are thinking about multi-copy measurements, we need to change our perspective. So instead of thinking about Alice and Bob having k copies of a unknown quantum state, we should think of them as having 1 copy of a giant quantum state. And of course, the states that they have a special structure, which is no matter which case they are in, Alice and Bob, their states is always of the form phi tensor k for some unknown quantum state phi. So these states are special in the sense that they belong to the symmetric subspace, which is defined as the set of states that are invariant under permutations of the subsystems. So an alternative definition of the symmetric subspace is the span of the states of the form phi tensor k. So the equivalence of the two definitions is actually non-trivial, and we refer to this reference by Harrow for a proof of this fact. So to understand what Alice and Bob can do inside the symmetric subspace, we need to characterize the measurements in the symmetric subspace, which is positive operators mi that sum to pi sim, which is the projection onto the symmetric subspace. In particular, we define the following measurement as the standard POVM in the symmetric subspace, which is a continuous POVM U tensor K, where U is a continuous state according to the Haar measure with some normalizing constant. So here du denotes the Haar measure, and the coefficient is the dimension of the symmetric subspace. So it is natural to understand this standard POVM from the perspective of the second definition of the symmetric subspace, because they share a similar structure. So as a warm-up, let's consider a very simple algorithm in using the standard POVM, which we can view as some sort of partial tomography. In particular, Alice and Bob, they both perform the standard POVM in the symmetric subspace and get some result U and V respectively. And next, they just compute a function of U and V. And this algorithm can be implemented with simultaneous message passing, because they can send the result to a third party who can compute the function. Interestingly, we can prove that this algorithm requires square root d copies to estimate the inner products. And this gives some evidence that maybe Alice and Bob cannot do better than square root d, because they are already using this very complicated standard POVM and still cannot beat the square root d bound. So now let's prove the lower bound. Let's consider a one-way protocol where Alice performs some POVM and obtains some result I and sends I to Bob. And Bob's goal is to distinguish which case they are in, either the same random state or independent random states. So from Bob's perspective, Bob knows Alice's message as well as what measurement Alice performed. So from Bob's perspective, there are two cases. In case one, when they share the same states, Bob's state will get updated after seeing Alice's measurements by this equation, because their states are correlated. This equation looks a bit scary, but it's just saying that Bob's state is no longer uniformly distributed because of Alice's measurement statistics. In particular, those states that have higher overlap with the operator MI will be more likely from Bob's perspective. And in case two, when they have independent states, Bob's state will always be the maximum mixed state inside the symmetric subspace, which is unaffected by Alice's message. So here, what we can prove is that when k is smaller than square root d, these two states are indistinguishable from Bob's perspective by any quantum measurement. And this implies a one-way lower bound. So next we show how to prove the indistinguishability. The proof is to think about the above state of Bob in case one as a output of the following quantum channel called the measure and prepare channel. In particular, this is just a new way to think about the state rho. So previously we have this measurement operator Mi, but now we just think of it as a normalized quantum state tau as an input to some quantum channel MP acting on tau. In fact, this measure and prepare channel is well studied in the literature. In particular, we can see that it is just measuring the state with the standard POVM and then outputs k copies of the measurement result. And using a result by Chiribella, we can actually show that the output of this quantum channel MP is actually indistinguishable from the maximum mixed state sigma m, regardless of the input state, when k is smaller than square root d. And this completes the proof for a lower bound against arbitrary one-way protocols. And interestingly, we show that this idea can also be generalized to prove a lower bound against arbitrary interactive communication, which completes the proof sketch for showing that square root d copies are necessary to distinguish between the two cases with any communication measurements. So that's all for the proof sketch, and I'll conclude by mentioning some open problems. First, our problem only considers classical communication, and it is natural to ask what could happen if we allow a small amount, say log n qubits, of quantum communication, and whether this could help reduce the sample complexity by a large amount. And second, it is interesting to prove upper and lower bounds for other distributed quantum property testing and estimation problems, and as well as estimating multiple properties at the same time following shadow tomography. And that's all. Thanks for your attention.